right, good morning, everyone. Shall I get started? Okay. So first of all, any questions from last time? Okay. So today we're going to talk about the second approach for building deep architectures. But let's start by reviewing what we went through last time, because I think there was a lot of things we talked about. So last time we basically said that we want deep architectures. Unfortunately, it's hard to train using backpropagation. And what happened in 2006 that revived the field is what's called layer-wise pre-training, where rather than doing backpropagation, which is you predict and then you update the weights in one full step, you do layer-wise pre-training, which is you first train the first set of weights using a unlabeled objective, so just trying to optimize the data likelihood. And after you've trained these weights, you fix it, and then train these weights. So all the data you propagate in, and next you keep these weights fixed and train these weights, okay? And we talked about one way to do it using restricted Boltzmann machines. And basically, that's the first way to do deep learning, okay? So the intuition basically is, if you want to do computer vision, first learn how to do computer graphics. In other words, if you want to do well on some task, first of all, learn how to model your data better. Okay, so you can view that each of these pre-training, adding hidden layers, is basically trying to find better ways to model the distribution of your input data. And by doing that, we can also exploit large amounts of data. Okay. So we talked about RBMs, restricted Boltzmann machines, and how stacking them together will form a deep belief net. So restricted Boltzmann machines look like this. It's simply a probabilistic function defined on, it's a joint distribution defined on the input x and the hidden variables h. It's simply some exponential where x and h have some pairwise interactions, okay? And this w basically indicates how correlated x and h should be. So if you have a positive element, that means both of them should be on at the same time. If it's negative, that means they should have different signs. If it's zero, that means they're not correlated. Okay. And we showed that once you know these weights, you can efficiently find the posterior distribution because everything factorizes very well. So basically, the posterior distribution of h given observing x is simply factorized as the posterior distribution of hj given x and the product of them. And this is simply a sigmoid over here, this sigmoid. Okay. So we showed that this RBM is very nice because you can compute this term very efficiently, which means that it's very easy to stack them into deep networks. But although this is easy, we found that computing the W is actually not easy. So if we want to optimize this RBM on the data probability or the data log likelihood here, going through the derivations, we get this simple equation in the end. But it turns out that one part of it is hard to compute, right? So this simple equation is basically, if we want to derivative of the log likelihood with respect to wij, is simply xi times j, the expected value of xi times j over the model probabilities, and the difference with the xi at the data point m times hj. Okay. And so we tried to visualize what this means. Basically, what this is saying is that when we have some initial probability distribution and we found that it's actually not the maximizing the likelihood of the data, what we want to do is we want to look at, okay, what's the probability of the current training point, and we want to increase it, and then what's the probability of some other points that are higher than this, but are not actually the training data, and want to decrease it, right? So by taking this difference, trying to improve this and trying to decrease this, then we can gradually try to maximize this log likelihood. Okay. Are there any questions about this from last time? Okay. Feel free to ask questions if anything is not clear. Okay, so that's how we can train RBMs, and the method is called contrastive divergence. So basically, it's a simple step where this is the pseudocode, but basically you can think of it as when you start here, when you get a data point xm, right? You set these values to xm, and then using the sigmoid equation, you can predict the h, right? This is your first set of h you predicted. Then given these, you go back and predict x again, and you go back and predict h again, okay? And the update is simply the first set of xh minus the second set of xh, okay? So that's called the contrastive divergence procedure, and you can think of it as trying to approximate what you would do if you actually try to optimize using Gibbs sampling. So Gibbs sampling will go back and forth until convergence, but now we just do one step. And that's cheaper to compute, and we want to do that because we're calculating this at each iteration of the gradient descent method. So finally, show that if we stack together these RBMs, we can form a deep network. Basically, stacking them together, and a deep network can be interpreted as this generative model. And you can actually think of it, if you view it in this way, you can actually think of when you have a deeper and deeper network, you're actually, in optimizing on the data likelihood, you're actually optimizing a bound on the data likelihood, and you can keep on improving it as you add more h's. Okay. But we also said that actually you don't need to have a generative model. You can simply take these weights and then initialize a deep neural network with these weights, and then use standard backpropagation to fine-tune the weights. And that does very well in practice. So when we talk about speech applications later today, we'll see that that's what they do. Okay. Yes? Yeah, okay. Yeah, so, okay, maybe I shouldn't say it. It's getting a bit complicated. So basically, you can think of it as before, when you have one layer, right? We are optimizing a log likelihood. And we don't observe the h's, okay? And by optimizing on the data likelihood, we're trying to find something that fits the data better. And once we fix this, next time when we fix this and optimize this, you can actually show that the log likelihood in this two-layer case will be better than this one-layer case once you fix this. Okay. Yes, yes, yeah, yeah. Yeah, although when you do contrastive divergence, everything's approximate, so all bets are off. Yeah. Yeah, but I guess basically I'm trying to say is that it seems very heuristic. You're just stacking together these, but there is some theory behind saying that you can stack them together and all of them is still a generative model, a probabilistic model. Yeah, but you don't need to actually worry too much about that if you just want to use them in some neural network. So we showed that, so this is nice just to use them as a neural network, but it's also nice if we have a generative model. So this shows an example of how a deep generative model can learn very well from data. So this shows that after looking at all these samples, the model can actually generate these images, which look very similar to real images, and that's actually quite amazing. Okay, so basically that's what we talked about last time, and what we're going to talk about today is an alternative to restricted Boltzmann machines called autoencoders. And autoencoders are nice because they're actually very easy to train. So you don't need this contrastive divergence procedure. and they're way faster to train. But you lose the probabilistic interpretation. So you can't have a generative model. When you stack together these autoencoders, you get something called a stacked autoencoder. And this is sort of comparable to deep belief nets in that they're deep stack layered networks. But although deep belief nets is a generative model, this one is not. Okay. All right, so today we'll talk about this and some discussions, and then we'll go down to applications. All right. So autoencoders actually is actually a very old technology, but it's been borrowed to use for deep learning. And the idea is very simple. You have some input data, okay? First of all, you're going to encode this input data into some hidden dimension. And then you're going to decode it back to the input space, okay? So the equation looks like this. The encoder is simply some sigmoidal mapping, right? It's the same nonlinearity we've been talking about. You have some x. You take the dot product with w. You get h here. And then the decoder here is simply taking the reverse operation, right? You can have the same w here, transpose, or you can have different w. Either one is fine. And what the autoencoder tries to do is to say, we want to make sure that this x and this x prime are the same. Okay, that's the objective you use to train it. So in other words, we will train this system on the loss like this. So for each point xm, we encode it and we decode it back, and want to make sure that it's equivalent to the original xm. Okay, because we want to minimize the difference here. Right, so that's the autoencoder square 2 loss. Does this equation make sense? Okay. And you can think of it as some sort of compression operation, right? Suppose you have some data, you run it through gzip, it encodes it into a smaller dimension, right? And then you run through gunzip, which puts it back to the original space. And if it's actually a good compressor, then you will not have lost any information. Or maybe you will lose some of the bits, but the remaining things still look very similar to this. So for example, JPEG encoding of images, right? You can compress a full image using JPEG very well, and when you look at it on the screen, it still looks very nice. That means it's a good encoder, right? So autoencoder is simply the same idea. Okay. So you can think of, we're going to call this object, after encoding and decoding, the reconstruction. Okay, we're just going to call this new guy, x prime, the reconstruction of x, because it's reconstructing the encoded x, right? And if you write out the equation, basically you put x prime, you put this term together with this term, then you get this term, right? Right. And what do you see here? So you see this term in this loss function. Does that actually look very similar to what we talked about before? It's just a 2-layer network, right? The 2-layer neural network that we mentioned. Right? You can think of it as this is the input and this is the output, right? So now you don't have any labels that the human gave you, but your label is basically the sample itself, right? So if the sample has 1, 0, 0, your label here is 1, 0, 0, right? And you can think of it's the same 2-layer neural network. You can just do back propagation with the labels 1, 0, 0 on this sample, okay? Right, so that's why the autoencoder is very nice, because we can use the same stochastic gradient descent algorithm, anything we've learned before, to optimize a single layer autoencoder. Right. Yes?
As a model, it seems very natural, but does it generalize to
So does it generalize to more layers? So basically, what we'll be doing is same as what we'll be doing for RBM. We do it for one layer, right? And then we fix the weights. And then we add a second layer and then train it there. So we always do it one layer at a time, and we can do that easily. Although you can think of a deep autoencoder, right? Where you have many hidden layers in between, and you try to reconstruct the output. And that might have the same problem as we had before. Okay, so we can stack them in the same way. And actually, this has the same form as the RBM before, right? So what's P of H given X? Basically, what's this given this, right? It's simply this equation. And what's X given H? It's this equation, right? So this basically has the same mathematical form as the restricted Boltzmann machines. And yeah, we can stack them together like this. But there's one big difference between RBMs and autoencoders, and that's autoencoders are deterministic, right? So in the autoencoder, we say that the value of H equals to this sigmoid, right? So basically, it's each of these H's is some value between 0 and 1, right? Based on this. But RBM, we actually say the RBM, it's defined as the probability of H is distributed according to this sigmoid function, right? In the RBM, hidden values, hidden nodes take 0 or 1 as their values. So here's the difference, right? So in the autoencoder, H can be any real number between 0 and 1. But in the RBM, it's only 0 or 1, right? So basically, in the RBM, you will compute this sigmoid. Maybe it'll give you some value, say 0.7. And then you'll flip a coin, and with 0.7% chance, you will get 1, okay? So it's a slight change of interpretation, but that's actually a big change in terms of how you can interpret these two different things, right? So these are simply nonlinear functions, right? But here it's actually a probabilistic model. Does that make sense? Okay. So when we do this, when we change to this, basically, because we lose this generative, because we lose this probabilistic interpretation, we can't form a generative model with autoencoders. But nice thing is it's fast to train, and we don't need to do sampling. Okay. Now, actually, can people? There's actually a very nice parallel between this autoencoder and the contrastive divergence algorithm. Can people kind of see it? So if you recall, in the RBM, we say that first of all, when we do contrastive divergence, we set X to be the XM, and then we sample H, right? And then we set H to be whatever we sampled, and then we sample X, and then we sample back again, right? So it actually looks like this, right? Given X, we compute H. Now, given H, we compute X again, right? So you can think of contrastive divergence with one step is kind of like doing the encode and decode operation, right? And the only difference is here H is continuous value rather than 0, 1. Okay? And the second difference is in contrastive divergence, the update equation is always based on some xi times some hj. But in the autoencoder, because of this loss, it's only based on the x term. Okay. So that's a slight difference. But basically, autoencoders were borrowed as replacements for RBM because people noticed this similarity of formulation. Okay. All right. So now there's actually many variants of autoencoders. And that's actually one reason I quite like them, because you can be very creative and try to define new things. So what we've been talking about, kind of implicitly, I'm assuming that your hidden variables, your hidden vector h is of a lower dimension than your input, right? So for example, here I draw, you always get smaller h, right? Because you're trying to compress the data, right? Now, if you actually don't have smaller h, in this case, say if h is also 4, like x here, or maybe you can look at here, right? So say we have 3 h's here and 3x. Actually, what will happen if we simply try to do this? If we have the same number of h's and same number of x's, under this loss function, what would be the optimal w? Yes, exactly, right? So basically, you don't do anything, right? You don't compress. It's an identity function, right? So all the weights, if we set it to be 1, we get the exact same thing here, and we can get exact same output, right? So that would be the optimal solution. And to prevent that kind of thing from happening, we want h to be smaller, so we can actually compress the data. We force compression on the data. So usually h gets smaller. But there's actually other ways to do it. Oh, so I should mention that if you actually, there's another variant, right? So here, this is a sigmoid nonlinear function, right? Now, if we actually take away the sigmoid and just make it a linear function, right, what will happen here? It's simply w times x, right? So basically, you get a linear function out. And it can be shown that if this is linear, then that's basically doing a PCA, principal component analysis. You'll get a result that's in the same subspace as what the PCA will get, because you're trying to reconstruct this square loss, which is exactly the same loss that PCA tries to do. Okay. So you can think of, you can use a neural network to get a PCA, although that's a very inefficient way to do it. Okay. So you can check out this paper if you want to know more. Okay. Now you can also have higher dimensional h. So this is actually a very exciting development recently is this idea that we actually have a hidden layer that's larger than the input. But we put some constraint on it, saying that although the layer is large, in practice, when you get the data, only a few of the elements should be non-zero. So we basically enforce sparsity. And the nice thing about this is that means that you can view it as an over-complete representation of your data. So you can represent your data with, say you have a 10-dimensional data, but you have 1,000 ways to represent this data, right? And there's some theory saying that you could actually get way better representations if you have this many things to use to try to represent data. Okay. And some people think that that's how the brain works as well, is this sparse over complete representation. Okay. There's also some work on making the hidden layers. So I said the hidden layers are, in our case, they are continuous between 0, 1, but you can also force them to be binary. And in that case, you can get some hash codes out, right? So you can use the autoencoder to train a hashing function. And that could be used for information retrieval. And finally, we'll talk about this thing called denoising autoencoders, where when you train the autoencoder, you add some noise to the training process. And you can add the noise by exploiting what you know about the domain. And that turns out to be a very effective way to train autoencoders. Okay, so we'll talk about it next. It's a very simple idea. So it's almost the same as the autoencoder, but you add noise to it. Okay, so now when you give your original sample x, okay, x is the original sample. first of all, you add some noise to it. It can be any noise. So you can add Gaussian noise, or you can randomly flip some of the bits, or you can randomly set some of the elements to 0. There's many ways to add noise. So you add noise and you get x tilde, okay? And then we actually try to reconstruct using x tilde. So we put the x tilde, the noisy version of x, into the encoder and then decode it back, okay? And the decoded back reconstruction, we want to make sure that it's actually similar to the original one without the noise added, okay? So you actually minimize the square loss, the reconstruction with the original. So you don't, the difference is reconstruction with the original rather than reconstruction with the noisy version, right? So what's this kind of thing doing, right? It's basically saying, okay, I'm adding noise to it, but I'm forcing my autoencoder to get rid of the noise after I train it, right? That's what you're forcing it to do. So by basically, here's a good example of how you can do it, right? So we talked about digit recognition in the first class. And we showed that, okay, digit recognition, most of it looks simple, but there's some problems, right? So if you shift the image, or if you scale the image, and you haven't seen that in your training data, then maybe it gets hard to classify. But now you can use that as a kind of noise, right? So for all the training data in your sample, you do random shifts, or you do random scaling, or random rotation to it. And after you randomly rotated it, you make sure that you reconstruct the original. So you're basically forcing the autoencoder to cancel out any rotation, any shift, and any scaling that you've done. And if the autoencoder, the autoencoder is trained to do that, and if it can actually do that, then basically you've learned some feature that's invariant to all these rotations. And that will be a very powerful feature, right, in your classifier. Okay. All right. So you can think maybe for your problem, right? Say if you work on speech, you can add noise to the speech, right? Add some reverberation, or add some sort of white noise, or reduce the decibel, right? And see, and still make sure to reconstruct the original. And then that means that if it can do it, that means the autoencoder has learned some invariance about the data. Right? Or in natural language processing, what people have done is, say you have a document, right, represented by a set of words. Now you're just going to randomly drop words in the document and force it to reconstruct those words. And if you can successfully reconstruct those words, that means that you've learned a deeper semantic representation. So that's the idea of denoising autoencoder. And it's called denoising because you add noise and then you try to denoise, take away the noise. Okay. Any questions? Yeah. The decoding weight is different from? Yeah, so the decoding part is sort of separate from the noise, right? So you can do anything you want here. I think you don't need to think that much. So basically, how you decode, it's basically this equation, right? So you mentioned decoding rate, or I'm not sure what you mean by decoding rate, but here we have samples, right? So for each sample, we encode and decode. So maybe you should think of encoding and decoding in the context of compression, so not in the context of communication, maybe. So we're simply a single data point, we encode it, and then we decompress it, decode it back. Okay. So there's no rate involved. Okay. Yeah. Did you have a question? Yeah. 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 Yeah, so that's a valid argument. So if you go along with the people who hype up deep learning, they'll say that, oh, we're going to learn features from raw data, right? We're not going to engineer anything. They do everything automatically. In that sense, then why do you need to add this noise, right? If you give enough data and your architecture is powerful enough, it should learn these things automatically. To some extent, that's true. But I think as a practitioner, it's always better if you have the knowledge, you just put it in, right? I mean, if you just want to improve your system, that's what you should do. Right? So this is one very modular and easy way to incorporate that. Okay. Yes? Mm-hmm. Oh, you think if you shift, maybe when this was original 1, this will become 1? Yeah. Yeah, it's possible, right? So you can think of it as, suppose this is an image, right? And you can have the pixel on here or the pixel on here. And so these weights will indicate whether this pixel is on or this pixel is on, right? And when you shift it, then maybe what's on here will be changed. And if you don't, if you have this kind of way to say that even though I shift it this way or I shift it this way, the output should be the same, that means that basically whether this was 1 or this is 1, it doesn't matter, right? So that will try to make these reconstructions to make it so that as long as one of them is 1, then we will make sure that this is 1. So that's kind of intuition. Does that make sense? So even though, I guess you're thinking, okay, how can I reconstruct if we shift, right? So that's an empirical question, right? And one way it might do it is to say that, so let's suppose input is 1, 0, 0. And when we shift it, it becomes 0, 1, 0, okay? But the output should be 1, 0, 0 here, right? No matter whether it's 1, 0, 0 or 0, 1, 0. It should be 1, 0, 0 here. Okay, so if that's the case, then this autoencoder is either going to make sure that whether, even if this shifts, this reconstruction, both of them will be high, right? So if either of them is 1, if both of these are high, then you can make sure that this is 1, right? That's one way to deal with it. Or you can maybe deal with it over here, so that if you shift here, whether you shift here or shift here, you make sure that this is always 1 if either of them is on, right? Yeah. Yeah, okay. Yeah, so if it's 1, 1, 0, then you get a different case, right? Of course. So then maybe you have 1, 0, 1, 1, and then that means that these have to be high as well. So I mean, it's possible that adding this noise makes it harder to learn the thing. But it's just something you try. So maybe in practice, people will have some parameters saying how much noise I add, and maybe they will vary it. And they'll find one setting of noise that will reconstruct very well. Yeah, yeah. You just kind of have to hope or trust the model to figure it out. Yeah. Mm-hmm.
I think it seems that the robustness of the model depends on what type of noise we have.
Yes, yes.
I mean, there are many types of noise in training data.
Yeah, yeah.
I mean, if we try to fit all the noise, we will have a strange model?
Yeah, it's possible. So you might, yeah, it's possible if you just add too much noise and you just can't fit it well, right?
Yeah,
that's entirely possible.
That is good to be added.
So it's really domain dependent, right? Right? So really, if you do image, people do what's called salt and pepper noise, right? So basically, you sort of sprinkle some pixels on it to sort of reflect, say, the camera pixel being on or off. But that's sort of a intuition kind of question. What kind of noise is good for your problem, and how much can you add to it? Yeah. So for example, in the image literature, and they've shown that using scale and rotation and all of that, you can actually get very good results. But there's some tricks involved as well sometimes. So maybe a simple autoencoder like this cannot deal with shift and variance. And if it cannot, you actually add a second layer on top. And later, when we talk about image processing, we'll see that something called a pooling layer that will, together with this, sometimes it makes it easier to model. Yeah. But that's kind of where research is, right? When you think about, okay, this is a basic model, and as a researcher in, say, speech or language, right, you think of, okay, what's the best in my case? Yeah. Okay. Any other questions? Uh-huh.
You say that this can be used as the automatic feature prediction, right?
Yes.
I still make sense that what is the feature in that model? I mean that what is the model budget?
What's the feature? So the feature is H, basically, right? This is a new feature you've learned. It's a combination of X. It's a new feature that's good at reconstructing your data.
In that case, the H is considered with the error noise.
H is what?
It's considered with noise.
H is, yeah, you can think of H is invariant to the noise, right? H is robust to the noise if you can successfully train this. So it's a feature that will be on even if you have noise. That's a good feature. Okay. Okay, so just to wrap this section up, so autoencoders are cheap alternatives to RBM. So we can simply train them using backpropagation. And just like RBMs, it basically focuses on modeling the data. Right? And the way it does is to say, okay, we want to model the data by first compressing a reconstruction and make sure that it's the same thing. Right? So that's how it focuses on modeling the data. Okay. And there are many variants. Okay. So that's basically all about autoencoders. Okay. So I think in this final section, I kind of want to summarize all of this, talk about why does deep learning work the way it is, when it works, and sort of give a bigger picture. Okay. All right. So why does layer-wise pre-training work? So this was a big question when layer-wise pre-training came out. And some of the hypotheses out there are like this. So Benjo and Erhan, for example, they say that if you think about a deep neural network, there's actually many ways in which this neural network can fit the training data, right? It can either fit by optimizing the upper layers or by optimizing the lower layers. Right? So basically, you have a very deep network, you give it some data, and you want to make sure it classifies correctly. Maybe that because there's so much freedom, you can either optimize the upper layers or optimize the lower layers. And that means that suppose you give the lower layers random weights. Okay, so meaning that the lower layers are just random features. Okay. Maybe your upper layer can still fit the training data very well because it's a very expressive model, right? But that means that these are sort of random features, and you cannot generalize well to the new data, right? So the reason that layer-wise pre-training works is to make sure that the lower layer weights are well trained in a sense, right? Because you start at the bottom rather than at the top. You start at the bottom and focus on modeling the data. You make sure that the lower level features that you learned are generalizable. Okay, that sort of works well on all the training data out there. Okay. Does that make sense? I mean, this is a very sort of, I think, a very beautiful hypothesis of why things work. So here's some results to support that. So they did an experiment. This is a online classification experiment. So there's no difference between training and test set. Basically, you give your classifier one sample, and it could be either positive or negative, and see does it get it correct. And then you update the weights right afterwards, and then you get a new sample again. And so this is showing the error it gets. So the lower, the better. And basically, they have a 3-layer network. So you can think of, it's kind of deep now, kind of make it hard for backpropagation. And they run for a lot of iterations. Okay. And this blue curve is just using backpropagation. Okay. So basically, whenever you observe a sample, and it's incorrect, you right away look at its label, and then you do backpropagation. And you see that it improved the error, but gradually it levels off. But this blue curve is a sort of pre-trained system. So for the first samples over here, it actually doesn't look at the label. Okay. So all these samples up here, so this is the number of samples, this system doesn't look at the label, but only tries to optimize the data likelihood. So basically trying to do pre-training up to this time. And after it's done pre-training, then it looks at the labels and does backpropagation. And then you see that at first you have a higher error rate than this guy because you only do unsupervised pre-training. But eventually you catch up, and then you can converge to a better optimum. Okay. Right, so this is basically showing that if you just wait a little bit, focus on modeling your input first, then after that you do backpropagation, you can get to a better area. Okay. So I mean, this is a hypothesis because no one knows for sure. So you can think of when we talked about deep learning, we said one of the big problems is multiple local optimum, right? So if you think of your loss function, if you have a linear or a one-layer network, the loss function is convex, which means that no matter which point you start out, you can make sure you get to a single optimum. But when you have a deep network, things are no longer convex, right? Which means that if you start here, you might get to this point. If you start here, you might get to this point. If you start here, you might get to this point, right? You'll get to different points depending on where you start. And basically, it seems like by doing pre-training, you can get to a better point. Okay. Now, we don't know whether this point is, which of these points it is, but it turns out to be better in terms of generalization error. And basically, this is trying to say that when you have a deep network, right? Maybe what's happening is that if you just do back propagation, you're focusing on optimizing these weights here. And you won't train these things at these first layers. And that will give you one kind of local optimum, right? But if you do pre-training, you will focus on these weights here first. And that will give you a different local optimum. And this kind of local optimum is better in the sense that because you've optimized on the input first, you actually have a feature that's more generalized. So that's the interpretation or the explanation they came up with, which is, I think, very nice. But you can actually, it's very hard to actually say for sure how it works. Okay. So that is a question. By the way, does that make sense? Are there questions? Okay. Yeah.
Actually, if you also do your pre-training, maybe you might also hold some very bad
Yeah, it's possible, right? So say you pre-train, and then you do back propagation, and maybe you get something like this, right? And that's so possible, because everything is non-convex. You actually don't know. But this is just empirically, people are finding that this is the case. So that's why pre-training people like.
Is there any way to, for example, to avoid this kind of error if you train? Sometimes maybe it's heavily.
So you say for pre-training, can you avoid pre-training not giving you this curve? I mean, it's possible. I don't know any work on this, but I mean, it's possible that you can have a supervised purely backpropagation system and then use that to feed information to your pre-training and make sure that you don't do something too different. I mean, that's possible. Yeah. Okay. All right. So is pre-training necessary for deep learning? If you ask the question in 2006, I would say yes. But if you ask now, you have to say no. So although I explained why pre-training can work, actually now the consensus is that actually it's not always necessary. So there are some new results now saying that if you just put enough data to the system, just do back propagation, you get good results. Okay. So basically, I think basically a lot of things have happened since the 10 years ago. So now we have more compute power, we have larger data sets, and so some of the problems that were considered hard before somehow just solve themselves as we come of age. And so there's two kind of things two kind of situations empirically. I mean, all this is kind of empirical. So if you satisfy any of these, maybe you actually don't need pre-training. So one is if you actually initialize the weights well, right? So earlier we said that maybe the lower weights, if we randomly initialize, it's like random features, and backpropagation will never update them. But maybe if you initialize so that you have sparse connections, right? And we actually will talk about this when we talk about computer vision. They actually do this kind of thing. So if you initialize it with sparse connections, and there's actually not that many that much freedom, then you can actually do things with a straight backpropagation. Or maybe if you have very large data sets, right? So if you're seeing so much data, then maybe you just won't overfit, right? So we said that maybe the previous hypothesis is that maybe we're just optimizing on the upper layers and making it sure that it fit well. But if you're seeing many, many training data, then the upper layer, just optimizing the upper layer might not be enough, right? So it seems like this is what we're seeing as well, is if we just have very large data sets, backpropagation doesn't have that problem. But actually, Hinton makes a funny, kind of interesting statement saying, but that just means that your deep network is not deep enough. So if you don't have these problems, you ought to make the network even deeper, okay, to make it more expressive. Okay, so that's kind of the state now is and everything I've taught you in the past 2 lectures could be wrong, basically. Okay, but basically that's the background. Okay, so as long as you know the background and you don't trust every single paper out there as truth, okay, and you actually try it out for yourself, and you use it as a guide. You use those papers as guide, but I mean things change very fast in this field. Okay. Okay. So actually, there's some new architectures that don't use pre-training at all. So for example, this stacked SVMs with random projections, they just have stacks and stacks of SVMs, and each of them is trained in a supervised way. Or in an alternative form, rather than using a deep neural network in the beginning, you start with a 2-layer neural network. After you've trained the 2-layer neural network, you insert a new hidden layer in the middle, and then you train that 3-layer network using backpropagation. And then you insert something in the middle again. And that's a way to, that seems to be a new way to do things for some problems. Right? And some product networks is also it's entirely different kind of probabilistic formulation. And so it's kind of, you can think of it as 2006, the field of deep learning sort of came about, deep neural networks and deep architectures were revived, and people are now exploring many new ways to do deep learning. Okay. Okay. So finally, I want to make some connections with other machine learning concepts. And so this is for people who know these concepts. If you actually don't know them, you can just ignore. Okay. But I think if you know them, it's interesting to see this connection. So you can, so for example, the RBM is actually a product of expert model. Right? So each of this hidden unit is like an expert, and each one of them is trying to explain the data. And because it's a product of expert, you can think of it as a distributed representation of the data. Right? So a data point, unlike clustering, which represents a data point as some space, a distributed representation will represent as multiple points in that space. And that's arguably a richer and more robust representation. So you can think of the origin, like clustering, for example, is like a mixture model, okay? And if you want to model a mixture model, use a mixture model to approximate the RBM, you will basically have to have to the n number of hidden components, right? So RBM has, because of the distributed representation, maybe three H's, but if you want to do a mixture model, it'll have to be 2 to the 3. Okay. So that's the difference of modeling power. Okay. And there's also some relations between, people have seen this a long time ago, relations between neural nets and SVMs. You can actually see SVMs as a 2-layer network, right? So you can think of it as in a support vector machine, basically your function is a linear sum of kernels. Right, so basically, it's a linear sum of whatever x you get, is a sum of kernels. And you can actually view this as you have the hidden layer is basically the size of the number of support vectors. Okay, so this is a hidden layer size of support vector. And this computation over here is basically like the kernel computation. So the first layer is the kernel computation, and the second layer are the weighted sums. Okay. And you can think of a neural network as learning the kernels of a SVM. And there's sort of papers showing that you can actually use a large margin like objective to train neural networks. Okay. Now, for people who know decision trees, you might wonder, okay, decision trees are very deep, right? So decision trees will classify the space. You can have many decisions on your variables. The difference is that decision trees are not distributed representations. So each data point gets, if you trace the path of the tree, it gets to one point. So unlike a deep network, which is a distributed representation. So actually, if you have a random forest or a bag of decision trees, you can actually, I think you can arguably call it a deep network. Okay. And then there's also philosophical connections to semi-supervised learning, for example, of exploiting unlabeled data, or curriculum learning of basically the idea that when you do a hard task, you first start by doing something easy, right? And multitask learning, right? So you want to learn features that can be shared between different subtasks. So there's a lot of connections. Okay. Any questions here? Okay. So finally, I will just talk about I think it's important to look at history sometimes. So people sometimes will call this the second revolution of neural networks, or the third wave of neural networks. And you can think of it like this. Basically what happened was the idea of artificial neuron was invented basically at the beginning of artificial intelligence. People were really looking at the problem of how intelligence can be created, right? So McCulloch and Pitts invented the artificial neuron, which is, you can think of it, it's very similar to this idea of we sum together inputs, and then based on some threshold, there's some output. Okay. And there's a way to train them, and that's all nice, but then sort of there's an AI winter, and this winter sort of happened to all fields of AI, where many negative results. People were very excited about AI in the beginning, but many negative results came up. People found that it was more difficult than expected. And for example, Minsky and Papert had a good book. And one of parts of the books, they showed that this sort of artificial neuron can only learn linear hyperplanes, basically. Right? And we've seen this in the first lectures. If you have only one layer, you can only get a linear classifier. And of course, life is not linear, right? So people sort of said, okay, this is too simple to work in practice. And in the 80s, there was a revival because people found that if you have two layers of these neurons, using backpropagation, you can actually train them. So basically, discovery of backpropagation, which is simply chain rule, right? But the discovery of backpropagation makes it possible to train two layers of perceptrons or logistic regression. And that makes it possible to approximate any function, right, given enough hidden units. So people got interested in it again. So a lot of work happened around this time. But then eventually people sort of got stuck, and they found that they can't train any deeper networks. So people move on to other areas like SVMs and Bayesian networks. And sort of, if you look at, there's this interesting plot. If you go to some NIPS papers, topic model paper, you'll see that the topic of neural networks boomed here and then gradually dropped in the 90s, replaced by these fields. And basically, we're here now. So people call it the second revolution. There's the first revolution and second revolution, where because of pre-training, people looked at this problem again, and amazingly, there's already products that use deep learning in them. And I think this speed is actually very impressive. So from 2006, in 5 years, there's already products out there that use this technology. So for example, a lot of speech recognition engines now use deep learning. And at Google, for example, the Google Plus photo tagging system also uses deep learning. So that's kind of where we're at now. Okay. I think sometimes it's important to not get too caught up in the hype. When you look at the history, actually a lot of people have worked on this problem in the past. Okay, any questions? So that's all I have to say about the sort of the background of deep learning. And after this, we're going to start talking about applications. Yeah. Okay. Mm-hmm. Current pitfall of deep learning. So I think you should think of deep learning as another toolkit in the machine learning field that you can use. Right? So you should just look at a problem and say, okay, should I solve it using SVMs or use deep decision trees, or maybe I should do a deep learning. Right? So if it candidate for deep learning is if it has a lot of data, right? And if the features, if you think that you can get better features using a deep architecture, then you can define by hand. Then that would be a good candidate for deep learning. Okay. Yes? Yeah. 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 Mm-hmm. Yeah, you can view it as that. Right? So, and whether you view that as it's just a better initialization, or that's an amazing way to initialize. I mean, that's subjective. Okay. Okay. Let's take a 3-minute break, and then we'll talk about applications next. Okay. Okay, let's get started. All right, so we're going to talk about applications now. In particular, I'll give 3 applications, one in speech recognition, one computer vision, and one in language modeling. And the idea of showing you these applications is to kind of give you a taste of how deep learning is used in practice. So we learned about RBMs and we learned about autoencoders. So how are they actually used in practice? And another goal is to actually show you how varied things are. So for example, you see that how things are used in speech recognition could be very different from how things are used in vision. So just to kind of let you know that, I mean, there's no truth in deep learning. Like, people are trying many different kinds of things. And for example, you see that in speech recognition, what's important is this hybrid deep neural network and HMM architecture. In vision, you see that this idea of local receptive fields and pooling, I mean, these are things that I'll explain later, but they turn out to be very important, right? And these are, I mean, very different things people are trying. Okay. By the way, I'm curious, over here, who here works on speech recognition or speech processing stuff? Oh, nobody, okay. About computer vision? Okay, a few. Natural language processing? Is it all, okay. How about other people? What kind of areas do you work in? Like weather forecast. Okay, okay. Yeah. Okay. So hopefully picking these problems is interesting for most people. Okay. All right. So first of all, I'll talk about speech recognition. So basically, I picked 3 different papers, and we'll just go through these papers. So first, I'll talk about this paper that appeared at the IEEE Signal Processing magazine. It's a very readable paper, so I suggest you read it if you can. It's basically by Hinton and a group of sort of speech researchers from different groups like Microsoft and Google and IBM. Okay. So it summarizes what happened up to then. So first of all, to give a background, sort of simplified view on speech recognition. The task of a speech recognizer is very simple. Basically, it's defined as given some input acoustic signal, you want to find the most likely word or phone sequence that's spoken, right? So you speak to your iPhone, and you want to make sure the iPhone actually can transcribe what you said. Okay, and this is usually modeled as such, right? So basically, it's modeled by 2 probability distributions, where you have first one is the probability of acoustics given the phone, and the second one is sort of a probability of phone sequences. So it's a probability of this phone given the previous phones. You can think of, we're going to try to optimize, given acoustics, we're going to try to optimize the phone sequence. Okay, so that's the basic setup of speech recognition. Does that make sense? Okay. If something doesn't make sense, please ask, because I might go a bit fast over some of the background. But I just want to give you enough background so you understand how deep learning is used. Okay. All right, so this is okay? Okay. All right. So in practice, this model here, the acoustics given phone, is usually modeled by what's called a Gaussian mixture model. I'll explain this later. In this phone sequence, you can think of it as being modeling by the transitions of a hidden Markov model, HMM. Okay. So here's what the acoustic features look like. So this is what the computer gets as input. So first of all, this is in time, right? So when you say something, you get this kind of waveform. And what people do in speech is, for this time series data, first of all, you take windows. So every 10 milliseconds or so, you take a window, and then in that window, you perform Fourier transform, okay? So that you can get the frequency components of each of these points. Because we know that if we know what frequencies are activated, you can kind of predict what sounds are being made. Okay, so this is a sort of a view, a spectrogram view of these frequency components. So here's time, and here's the frequency axis, and red means that that frequency is active. And from this, people do some signal processing to extract features. So for example, they take the log of this, and then they take some other processing. But basically, what comes out is usually some sort of 40-dimensional vector. Most often used is something called Mel frequency cepstral coefficients, MFCCs. But basically, you can imagine the input to a speech recognizer is the feature goes through a sequence of processing, and it's about 40-dimensional vectors per 10 milliseconds. Okay. And this is the input that this Gaussian mixture model will have to model. Okay. So for one kind of phone, it will have one kind of, you assume that it will have some kind of feature vector. Okay. So in a nutshell, should I explain that more? Maybe I should explain that a bit more. So you can think of, say you make different sounds, right? So you make ah, right? When you open your mouth and make ah, the ah sound. That will have a certain kind of frequency characteristics. And with that kind of frequency characteristics, you have maybe some kind of vectors coming out, right? So maybe it will be, these parts will be large, and then these parts will be small, okay? So maybe at certain frequencies, it will be high. And then say you do E, right? E, that'll be another set of kind of vectors that will be produced, okay? And now we're not going to consider time, okay? So in practice, time is important, but let's just say, let's look at this time instant, we get one vector, and what does it look like? So maybe the part here is strong, and then E, the part here is strong, okay? And basically, you want to try to model this. So you want to have a probability model of this vector given and you have a probability model of this vector given E, right? And so if you can have a good probability distribution for each of these, then when you get a new sample, so you get a new sample that looks like this, then you can say, oh, okay, it looks like an ah, right? Now in practice, so how would you model this thing, right? It's a 40-dimensional vector of continuous features. So most natural is a Gaussian, right? So you can say, okay, a Gaussian has a mean value and a variance, right? So to model this, you can say that, okay, ah is some Gaussian with mean here. Here the means are high, and then here the means here are 0, right? And then variance is some kind of variance. Right, so that would be some Gaussian model, and E will be another kind of Gaussian model with a different mean. Okay. And to calculate that, basically you will take all samples of A and then take the mean of the vectors, then you can get the mean of the Gaussian. But it turns out that using a single Gaussian to model speech is very hard. So in practice, you get, maybe you actually have multiple places be active. Right. So when you look at samples, you see many things. So people would use multiple Gaussians to model this one sound. Okay. So if you look in the two-dimensional space, right? So let's put this vector in the two-dimensional space. So maybe the vector, if your data looks like this in two-dimensional space, you can use one single Gaussian to model it. right? This is a Gaussian. But if the data looks like some disjoint sets, and actually it kind of looks like this, right? So R maybe looks like this, E maybe looks like this. So in that case, you use 3 Gaussians and the sum of them to model A, and then maybe use these 2 Gaussians, sum of them to model E. Okay. So that's how acoustic modeling is done. Are there questions here? Okay. And basically, that's the state of the art in speech recognition is that Gaussian mixture model. And on top of that Gaussian mixture model is a hidden Markov model, because you want to, you know that, say, after you say ah, you kind of know what's the next word coming, right? So you want to model transition. So for example, I say, today we're talking about deep, and what's the next word I'm going to say? Learning, right? If I say deep, I don't know, deep sleep or whatever, right? That sounds kind of strange, right? So you can have a HMM the hidden Markov model will model the transition. Okay. So basically, what people do in speech is this. You can think of, so here's the features that we're trying to model, and if you plot these in some space, they're very complicated. So you use a Gaussian mixture model to model this phone to output phone to speech acoustic distribution. Okay. And then on top, you have this hidden Markov model to model the transition of the phone states. Now, what people are doing in deep learning is simply to replace this Gaussian mixture model part. So the top part of using hidden Markov models is still the same. It's only this part. Given this state, what's this output or this input? That part's been replaced by a deep neural network. Okay. So that's the only part that's changed, but that's actually been showing a lot of improvement. Okay. So you can think of it as a hybrid model, right? It's a hybrid deep and hidden Markov model. So what people usually do in practice is they use deep belief nets to train. So basically, people will use RBMs, not autoencoders. So you use RBMs, stack them up, and 3 to 8 layers of RBMs, maybe 2,000 units per layer. And this RBM, the input to the RBM will be a 15 frames or so of input. So you actually are taking input over time and putting them all together. And that actually turns out to be very important. So when you do the Gaussian mixture modeling, people take 1 frame here, right, to model. So each frame is sort of modeled independently in that case. But in a neural network, you can put all that information together. So you can use the previous information, the future, not the future, but you can use the ones on the right and the left. Okay. Okay, so the output space here is the number of phones. And people usually do something called triphones, which is they take into account the previous context and the next context, because that changes the shape of the frequencies. And maybe typically thousands of output labels. Okay. Okay, so the way to train it is, first you do a supervised pre-training on just the speech input. After that, you use that to initialize a deep neural network. And the labels you get here, these could be automatically derived by some original system. So some original system could actually get these labels. So these are rough labels for you, and you can do backpropagation. And then further, after you do that, you can actually do discriminant training in conjunction with this hidden Markov model. So you can sort of take the posteriors here and then use that as to update here. If you don't understand that part, it's okay. But basically, you can think of everything people have done trying to do discriminant training. All the training procedures here can be applied here as well. Yeah.
So if we use deep neural network, we will have the frame overlaps each other.
Yeah. Yeah, so they actually have frame overlaps. Yeah.
And now the question is, how we define the subset frame is a parameter, or we learn
So here, usually people set it, right? So it's a hyperparameter people will say, okay, how many frames I'm going to take. Yeah. So the reason they can use a lot of frames here but not here is when you try to use a Gaussian mixture model, right? If you have successive frames, they're going to have correlations, right? Because this frame is going to correlate with the immediately next frame. And when you have a correlation, that means in this feature space, things will get diagonal, right? So if you want to model a diagonal well, then you need to make sure you have the variance. And turns out if you want to model the mean of a Gaussian, it's very easy. But if you want to model the entire covariance matrix of a Gaussian, that's a lot of parameters. So people usually don't use multiple frames. Yeah. Okay. Are there questions here? Does it make sense, even if you don't do speech? Okay. All right. So one thing I should mention is that here the speech signal input is a continuous value input, right? So when we talked about RBMs earlier, we're assuming that both of these are binary. So there's a variant of RBM called Gaussian Bernoulli RBM that can handle this being a continuous data. And that's what it looks like. H is still binary, but now X is a real value, okay? Continuous variable. So it's actually almost the same formulation. P of XH now, so it's the same exponential form. And now you define this energy function here like this, right? So you can think, I mean, it's a very natural way to parameterize it. So you say, this is sort of the Gaussian term, right? Xi minus the mean of this part, this Bi, and divide by some variance, right? So this looks like a Gaussian, right? If you just look at this part as a Gaussian. Right? And again, here's the interaction term. Right, the interaction between X and H. So that's the same as before. The only difference is you have some normalization by the variance here. Okay. And this part is the same, right? This is a bias of the hidden units. Okay. And so given this form, if you want to compute the posterior of H, it's almost the same sigmoid. Right? You just basically sum together all the X's, sum together all the X's, and you can get H. Okay, so just some normalization. And so now if you know the H and you want to predict what's the probability of X, it's basically a Gaussian with a mean that looks like this. So again, it's very similar form. You just do a weighted sum to get this. And yeah, so that's the Gaussian Bernoulli. So basically, just to show you that you can do continuous data with RBMs. Okay. And usually, so here's a variance term here. Turns out it's actually hard to learn this variance. So people usually just normalize the data to be zero mean univariance before they train this RBM. Okay. So that's just a detail to show that you can do continuous data. Yeah, but this is just the first layer, right? So once you train this, everything else in the end is binary, so you can use the same RBMs. Okay. So why is a deep neural network good in modeling speech? I think arguably you can think that speech is actually produced by only a few number of parameters in your vocal tract, right? When you try to say it, there's only you can't really change your lungs that much, right? You can't change your throat that much. So although the signal we observe is very complex, the true structure actually is in some low-dimensional space, right? So the question is, how do you extract this low-dimensional space, right? And when you use a Gaussian mixture model to model this kind of data, I mean, basically what you're saying is this, right? you're saying this is a Gaussian mixture. So it's basically a sum of Gaussians. These are Gaussians. And you can think of a Gaussian mixture model, basically you're placing circles, multiple circles over your data and trying to model it that way. And it's actually very expressive, right? So any kind of, you can think of any shape of data, you can model it as long as you can put infinite many number of circles, right? So in terms of model expressiveness, the Gaussian mixture is very good. The only problem is that you might need infinite number of Gaussians. Right? So in particular, if you have a sort of a diagonal kind of data set, you either need a Gaussian that has the full covariance term, or you have to have many small Gaussians, right, to model that. But using a RBM, because of this mixture of experts interpretation I mentioned earlier, you can actually model the same space but with fewer number of parameters. And that's one reason why DNNs are better than Gaussian mixture models. Okay. So in terms of, basically what I'm trying to say is, in terms of model expressiveness, they are kind of the same. But in terms of the data and the number of parameters you need, you can have more compact representation using a RBM. And because it's more compact, then maybe you can do better with less data. Okay. So then let's just look at the results. So these results are from the paper. They have more results. It shows the word error rate. So this is, you can think of how many words is recognized incorrectly. So lower, the better. Right? So this is basically saying, kind of, in a sentence, 18% of the words were incorrect. Okay. And these are different tasks in the speech community that people have worked on. And here it shows the number of hours of training data that people have. So some of these are quite large. And here's the result of a deep neural network, hybrid deep neural network with HMM, and the GM-HMM. So Gaussian mixture model with HMM. So these two are using the same data, just to do a direct comparison. And you can see that for all these data sets, you get big improvements when you switch to a deep neural network. Okay. So people were very excited about this kind of result. I mean, if you work in speech, that's amazing improvement. Because people have been working very hard to get 1 point improvement, right? But I mean, that's a big improvement. Okay. And here it shows if you use the GMM, the Gaussian mixture model with more data, I mean, you can get close. But so that's basically, it's not, it needs more parameters to model, right? So if you have more data, maybe you can catch up using Gaussian mixture models, but this is more compact representation. Okay. And actually, it turns out that why it works, people found pre-training didn't matter that much. Pre-training improved results, but it seemed like using a larger context, so using that 15 frames and using fewer pre-processing steps turned out to help. Okay. So here's some, just more in detail, just to give you a sense of what's going on. So this is from this paper on the switchboard task, so on this first task. Basically, their input to the DMM, to the DNN neural network is sort of 40-dimensional vector. And the output space they want to predict is about 9,000. Okay. So these are the things they want to predict, different kinds of phones. A standard Gaussian mixture model, you have to have about 40 Gaussians per phone, which is actually quite large to train well. In the deep network system, they have 7 stacked RBMs. Each of them is about 2,000 units. So here they do pre-training. Pre-training, they do 2 passes of pre-training over the data. And that's actually a lot. It takes a lot of time. So there's a lot of work on how to speed it up. Oh, okay. next time we'll talk about speeding up. So for example, using GPUs and things. Here's a feedback. But here's the results. So basically it's showing that this is your original Gaussian mixture model system. If you just use a single one-layer network, you get worse. But actually, if you add context, you add more context in your network, you can get better. And then if you do a deep system, you get even better. Okay. And then here are some other modifications. Okay. But here the biggest gain is from this larger context and the deep network. Okay. All right. So are there any quick questions? I realize we're out of time. Okay. If not, so let's continue on computer vision next time. All right. If you ask questions, get your questionnaire. Okay, see you Thursday.